Hello, and welcome to this presentation, Understanding POCSAG. In this presentation, we'll provide a short technical introduction to POCSAG paging, including both RF characteristics, as well as the format of POCSAG messages. Let's start by explaining paging. The term paging can refer to a family of unidirectional radio messaging systems that can transmit simple tone alerts, numeric messages such as phone numbers, as well as alphanumeric messages. Pagers typically alert users to an incoming message by vibrating or by playing a tone or beep. And this is why pagers are sometimes referred to as beepers. Paging systems are operated in many different frequency ranges, but most often these are found at VHF, UHF, and in the 900 MHz band. Exact frequencies vary both by provider and by geography. Note too that a service area may be covered by a single paging transmitter or by multiple transmitters that send the same messages simultaneously. Paging has a number of advantages over other radio communication systems. The most important of these is that paging excels at providing reliable and robust coverage over larger geographical areas. Paging also provides excellent in-building coverage, especially compared to cellular or even two-way radios. Another significant differentiator of paging over cellular or two-way radio is that pagers typically can run for a month or more on a single, easily replaceable battery. We'll explain the reasons for this in more detail later in this presentation. Most commercial pagers are also relatively easy to use. Simply press a button or two to silence a page or read a message. Pagers tend to be physically robust as well. Furthermore, pagers are much less expensive than most other communications devices. Since paging is generally a one-way system, receivers cannot be tracked or traced the way cellular devices can. But it's important to note that paging messages are not normally encrypted and can be easily intercepted and read. And finally, paging is very spectrally efficient, requiring at most about 25 kHz of bandwidth per paging frequency, and thus licensing requirements and cost are significantly lower than for other radio or cellular services. As mentioned earlier, one of the first uses of paging was sending phone numbers. The user would receive a page containing a phone number and then would call that number from a landline or mobile phone. Numeric paging was later expanded to alphanumeric messages. These were usually personal messages for a specific user or subscriber, but some paging providers also offered information services, such as short updates on news, sports, etc. Although paging is not as common as it once was, it's still very widely used in healthcare. Paging is also found in emergency or public safety settings due to its long range, reliability, low cost, and the ability to send messages to groups of recipients. One less-known application is pages that are sent by unattended systems when an event or alarm occurs. For example, an unattended system could send a page when a generator begins to run low on fuel, or when a door is opened. And finally, amateur radio operators have repurposed commercial pagers for non-commercial applications, the best example of which is DAPnet, or the Decentralized Amateur Paging Network. Several different paging protocols have been developed and deployed worldwide, but the most common of these, by far, is called POCSAG. POCSAG is an abbreviation of Post Office Code Standardization Advisory Group. This standard was developed in the United Kingdom at a time when the Post Office was also responsible for telecommunications, and this is why the words Post Office appear in the name. The current standard is CCIR Recommendation 584-1, Standard Codes and Formats for International Radio Paging. In the remainder of this presentation, we'll provide a brief but technical introduction to POCSAG, including both RF characteristics and the structure of POCSAG messages. Let's start with modulation. POCSAG uses binary frequency shift keying, often referred to as 2FSK or BFSK. This simple form of modulation is easy to implement, and is largely responsible for POCSAG's wide coverage area and good penetration. In FSK, the signal or carrier switches rapidly between two frequencies. One frequency represents a logical 0, and one frequency represents a logical 1. The distance of each of these frequencies from the nominal center frequency is called the deviation, and POCSAG supports two different deviations, plus or minus 4.5 kHz, or wideband, and plus or minus 2.5 kHz, or narrowband. Using the narrowband deviation allows for tighter channel spacing. Note that in POCSAG, the higher frequency is the logical 0 or space, and the lower frequency is the logical 1 or mark. This is the opposite of most other 2FSK applications. POCSAG sends bits at one of three standard bit or symbol rates: 512 baud, 1200 baud, and 2400 baud. Lower baud rates improve reliability and increase transmission distance, whereas higher baud rates reduce overall transmission time. That is, they enable more pages to be sent per second. Transmission rate is fixed throughout a paging system, so the paging transmitter and all pagers must operate at the same baud rate. Pagers must therefore be configured with both the parameters of the paging system as well as values which identify a specific pager. This is normally done via a special hardware interface and software package, although some more modern pagers allow users to directly configure these parameters on the pager itself. The four most important configuration parameters are the nominal frequency, the baud rate, the bandwidth, that is, narrowband versus wideband, and the Capcode. We've already discussed the first three of these parameters, so now let's explain what we mean by a Capcode. The CAP in Capcode stands for Channel Access Protocol, and the Capcode is a unique ID assigned to each pager in a system. The Capcode is often given as 7 numeric digits, although the Capcode itself is 21 bits long. The most significant bits are the address, and the three least significant bits are the frame location. We'll explain these last three bits in more detail a bit later in this presentation. Originally, pagers could only be programmed with a single Capcode, but more modern pagers often can support multiple Capcodes. This is particularly useful when the same Capcode is assigned to multiple pagers, since this enables both individual and group paging, that is, sending the same message to multiple pagers simultaneously. Now let's look at how bits are transmitted. All POCSAG transmissions begin with a preamble, which is then followed by one or more batches. Every batch starts with a special frame synchronization codeword, which is then followed by 8 frames. These frames in turn each contain 2 codewords, for a total of 16 codewords per batch. Over the next few slides, we'll explain each of these fields in much more detail, starting with the preamble. The preamble is a sequence of at least 576 alternating ones and zeros. It both signals the start of the POCSAG transmission and also signals the baud rate. If the POCSAG signal is audio demodulated, this preamble is what produces the short audible tone at the beginning of a transmission. One reason for using a long preamble is that it allows pagers to extend their battery life by sleeping or entering a low power mode between pages. If the pager wakes up and does not detect a preamble, it will go back to sleep, whereas if it does detect a preamble, the pager will then sync to its baud rate. All bits following the preamble are sent at this same baud rate. Immediately following the preamble is the frame synchronization codeword. This 32-bit word contains a special fixed bit pattern. Each batch of 8 frames is preceded by this codeword. Note that if multiple contiguous batches are sent after a preamble, then each set of 8 frames must be preceded by an additional frame sync codeword. Within each frame, 2 types of 32-bit codewords can be transmitted: the address codeword, which starts with a 0, and the message codeword, which starts with a 1. As the names imply, the address codeword contains address bits, and the message codeword contains message bits. The address codeword also has a pair of function bits, but the use or meaning of these bits varies between paging systems. Both types of codewords end with a 10-bit BCH error correction code, and a single even parity bit that protects the entire codeword. Note that in addition to the framesync codeword, address codeword, and message codeword, a special idle codeword also exists. This codeword has a fixed bit value and is used to fill any unused codeword slots or as the last codeword in a transmission. Let's take a closer look at address codewords. After a pager detects and decodes the preamble and framesync codeword, it then starts looking for its own capcode inside of an address codeword. Address codewords can appear in any of the 8 frames. But to save power, a pager will only look at one of the 8 frames in each batch when searching for an address word containing its capcode. Which of these 8 frames the pager wakes up for is determined by the 3 least significant digits of the pager's address. This is the frame location we mentioned earlier in the presentation. These 3 bits map to 8 possible frames. For example, if the last 3 bits of the address were 011 or decimal 3, then the pager would wake up during frame 3 to look for its capcode, but it would be sleeping during the other 7 frames. This mechanism is one of the main ways by which POCSAG extends battery life. Every address codeword is immediately followed by one or more message codewords, and these message codewords contain the message content for the addressed pager. If a message is too long to fit in a single word, the message may be spread over multiple codewords, and even over multiple batches. For example, this batch contains 4 messages. The first requires 5 message words to transmit, whereas the second and third need only a single message word, and the fourth uses 3 message words. The end of each message is indicated by a new address word, or when the special idle codeword is detected. Note that the arrangement and order of messages and codewords is dynamic and will change from transmission to transmission. Before we end this presentation, let's briefly discuss how POCSAG pagers are tested. Special test instruments called radio test sets can be used to send pages to the pager under test, and this can be used to verify pager RF specifications, such as sensitivity and selectivity, as well as the rejection of spurious or image signals. Another aspect of pager testing is power consumption, which can be measured using a precision power supply or source measure unit. The goal in this scenario is to determine the current draw in both active and standby operation. In many cases, these characteristics are a function of parameters such as baud rate, message type, etc. Let's end with a brief summary. Paging provides reliable, low-cost, unidirectional messaging over wide geographical areas and with good in-building penetration. The most common paging protocol, by far, is POCSAG, which uses 2FSK modulation at rates of 512, 1200, or 2400 baud. Pagers and messages addressed to them are identified by a unique capcode. The transmission format of POCSAG messages begins with a preamble, followed by a framesync codeword, and then one or more batches. Each batch in turn contains 8 frames with 2 codewords each. Address codewords contain the address of the called pager, whereas message codewords contain the numeric or alphanumeric message for the addressed pager. And finally, the types of tests performed on pagers fall into 2 general categories. The first is RF performance, such as sensitivity and selectivity, and the second involves measurements of power consumption in both active and standby modes. This concludes our presentation, Understanding POCSAG. If you'd like to learn more about POCSAG testing, or about the instruments that can be used in testing POCSAG pagers, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rody-schwartz.com.